Hello everybody, welcome back to another Gregorious Maths video. And well yeah, it's been a little bit too long since I've done a video, but that's okay because I'm back now. And well, I'm excited to announce this slightly more formal, you could say, series that I'm going to be starting, and it's about classical homotopy theory. And so I was going to include, some aspects of more abstract homotopy theory, going to like more categorical perspective. And that was originally the plan. It was going to be like a whole part on model categories, and I was going to go into a little bit of simplicial sets and even quasi-categories maybe, but instead what I've decided to do is I'm going to do classical homotopy theory. In the introduction I'm going to explain, the contents and a little bit of the format and stuff. And then I've just started a reading group for Categorical Homotopy Theory by Emily Riehl, which is a good book, and that's how I'm going to record either just my own thoughts afterwards, or the actual online meeting, and put those onto YouTube for the more categorical side for homotopy theory. So I've got different colours here for, okay, so I should probably explain the format. So except for this video, for every single video in the series, it's going to be proper like format, so I'm going to literally have notes in my hand, and I'm going to be explaining them obviously and writing it down and stuff. And then afterwards I'm going to post the notes themselves for the video, and it's going to be in an extra blog post which covers something that I found which is simply just interesting, related to the topic which I just did a video on, or something extra which might actually be used in another video. So for example, for the categorical preliminaries, I intend on just talking about, so in the actual video talk about the main concepts of category theory, and then for the blog post I'd post the notes, and then also talk about how the category of categories is a two category, which I won't need for any of this other stuff, but it's quite an interesting extra remark, and it could inspire further reading or whatever. As an example of something which might be used later on, at the very end, when I talk about Steenrod squares and Steenrod algebra, I focus on the mod 2 case, and then in the blog post I plan on talking about how you can generalize this to the mod P Steenrod algebra, which actually I will be using this case for the Adams spectral sequence construction. So that's an example, although those examples are going to be hopefully rare throughout the series, but just look out for the blog post too, which will always be in the description. So okay, so for the introduction I thought I would go through the table of contents, which I've written down, and also the preliminaries for this series. So okay, I've got different colours for the different kind of broad sections, you could say. So this blue section here is kind of like the very basics of homotopy theory, the stuff that we're going to be using throughout the whole series. So obviously categorical preliminaries needs no explanation. Even though it is classical homotopy theory, I will be using category theory throughout, so just hammer those down. Won't be assuming any knowledge of category theory, although it would be nice, but strictly not assumed, because of this video. Then obviously I go on to the main study of homotopy theory. So I will be assuming that you know what a homotopy between two maps is, or a homotopy equivalence or whatever, but I won't be assuming that you know the definition of pi n. So I'm going to be talking about what homotopy groups are, and of course that's vital for the rest of the series. Then I talk about loop spaces and suspensions. So this is an interesting topic here to cover, and I choose it directly after this because it requires minimal preliminaries, and it provides us with an interesting description of homotopy groups, which nicely links back to the video there. Also, suspensions are going to be used a lot here in this video about spectra, where we discuss stable phenomena. Of course, suspensions are going to be vital. Loop spaces in general, you know, they come up everywhere in homotopy theory, so, and also because of the loop space suspensional junction, it would be silly to talk about suspensions without talking about loop space. Then I go on to another vital aspect of homotopy theory, which is co-fibrations and vibrations. And again, these things are used often. You know, they give rise to one of the most important long exact sequences in homotopy theory. So again, a vital topic and something which, you know, I intend to cover nice and early, just in case, you know, it comes up at a later point. For example, stereospectral sequence, it's of a fiber, you know, comes up there, and I'm sure it will come up other places which I can't think of at this very moment. The Horowitz theorem, again, this is just a very important theorem which has a lot of applications. It links homology and homotopy, so I will be assuming you know what homology groups are and cohomology groups are, but not what homotopy groups are. And the Horowitz theorem is a way to link these two groups. So that's a very interesting thing to note. It is quite revealing because, you know, it shows that these two things are not unrelated. And it links in nicely with the categorical preliminaries because it, of course, the Horowitz homomorphism is a natural transformation. And also, we use it in the spectral sequence area when we're setting up a connection between spectral sequences and homotopy groups. And lastly, I'll be covering the homotopy excision theorems. Again, these are just really useful theorems. The Freudenthal suspension theorem will be in this video, and again, that will be vital when studying stable phenomenon because, you know, that is literally a theorem which tells us exactly what happens as you iterate the suspension a growing amount of times. Then, okay, so those are the 6, you know, kind of basic videos there. I shouldn't say basic, but like the fundamental ones. This is kind of introductory homotopy theory here. And again, keep your eye out for the blog posts because they could contain some interesting additional information about these topics. Then we move on to these 3 green things here. Now, what are these? These are going to be topological K-theory videos. So the first one is going to be the first few definitions in topological K-theory. So this is going to be strongly following my fiber bundles talk, which I gave a long time ago, when I briefly touch upon K-theory and vector bundles and so forth. So that's the type of thing I'm going to be talking about, and, you know, kind of you know, going over some examples, going over some definitions and so forth. Then, number 8, this is what I'm calling Bott periodicity twice. And, of course, the main focus of this is Bott periodicity. But, of course, really, this twice here suggests that we're going to be looking at two different perspectives to topological K-theory. And indeed, that's what I'm going to be doing. I'm going to be looking at it from a more cohomological perspective, so as a cohomology theory, but also, you know, that other way of looking at it as the, you know, some classes of homotopy groups between, you know, this and that. And again, this is going to nicely tie in with the spectra, because they describe homotopy groups, generalized cohomology theories, which of course K-theory is, and so, you know, links are there as well. So, you know, this really Bott periodicity is because that's a vital theorem in K-theory, but really the main focus of the talk is to expose the different ways which we can look at topological K-theory. And then, of course, we wouldn't want to just talk about K-theory and move on. We kind of want to see why we've been talking about this in our homotopy theory series. So, why am I blabbing on about K-theory if it's no use in the homotopy theory? So obviously, I'm going to be covering why I'm blabbing on about it in this video here. Now, okay, we have a brief interlude, I'd say. I don't think this really fits this spectra. I could argue it fits in here because, well, I'm using it to describe K-theory in general, generalized cohomology theories, and I could argue that it lies in here because, well, the Adams spectral sequence It's kind of based on spectra. But I don't really think it fits in either of these. This is kind of the beginning of stable homotopy theory. And that's a very important branch of homotopy theory, of course. And spectra, well, what they do is they study what happens, what the stability of, in general, the category top under suspension. And, well, what's really nice about them is that they describe generalized cohomology theories at the same time. So they enjoy some nice properties. In fact, in the blog post about this, I intend on talking about some... Oh, dearie me, I can't stand. I intend on talking about some technical issues, some technical details about spectra which I might miss out in the actual video itself, and that should also be quite fun, too. Then the purple part, this is the kind of last part of the series, and it's going to be talking about spectral sequences. So, we have the introduction to spectral sequences, so these are some basic definitions, basic ways to construct spectral sequences, which will also be important. Number 12 is the Bochstein spectral sequence. So I'm going to mainly be covering the construction, and perhaps a few applications too, but mainly this one is going to be focused about the construction. It's a very constructive example of how to construct a spectral sequence. Now the series spectral sequence. I anticipate that this video is going to be pretty long, just because there's so many applications of the series spectral sequence that I can't help myself to go into detail about quite a few. And yeah, so in fact, I'm going to be talking about how the fourth homotopy group of the 3 sphere is the integers mod 2. And I know I've already done that in a previous talk, but for those of you visiting my channel now or after this, you might not have seen that. So, and again, it's a lovely use of the Hurwitz theorem and spectral sequences in order to get results about homotopy theory, which is the whole point of this. Then I take a brief interlude. This isn't really strictly a spectral sequence, but I talk about cohomology operations and the Steenrod squares. And the reason that I do this is, first of all, they're a really interesting topic, and they come up all the time in homotopy theory in general. But because I want to talk about this atom spectral sequence here, and the atom spectral sequence is constructed very much on cohomology operations on the Steenrod squares, and we're linking back to the Eilenberg-MacLane spectra here, as you'll see when we eventually get there. And then the final video will be about homotopy groups of spheres, and the reason for this is homotopy groups of spheres have inspired, not all of it, but a lot of this machinery which I'm going to be covering in this series. And so it would be unfair to completely leave out this as a topic. So I thought I would do the last video where we exploit as much machinery as possible, and we try to compute as many homotopy groups of spheres as possible. And so hopefully this kind of brief tour of the contents, gets you excited. That was going to be my outro, but I just remembered that, I forgot to kind of go over the preliminaries. So preliminaries, I would assume a knowledge of homology groups, cohomology groups. Those are the main ones, really. Category theory is not assumed. Group theory definitely assumed. I'd say don't worry too much about the preliminaries, as long as you have a... I would definitely not be watching the series if you don't know topology at all. But if you have a firm-ish grasp on topology, and maybe you've heard of and have looked at a little bit of category theory, and you know a bit of group theory, and you know a bit of this and that, then I would just go ahead and straight away and watch the videos. You can always pause, you can always come back to it, you can always look up definitions in the middle of the video. I'm not gonna come to your house and do God knows what while you're sleeping. If you do that, So yeah, hopefully you guys enjoy this series as it unfolds. I'm quite excited to be presenting it to you, and keep your eyes peeled for these videos, the blog posts that go with them. I'm going to try and keep up the homological algebra series, you know, that'll just be, again, you know, that'll be the same format as it was, you know, 20, 15-minute videos, just mostly improvised, not as formal as this, and keep your eyes peeled for the categorical homotopy theory reading route, as well, so keep your eyes peeled for a lot of different things which are hopefully going to be coming during the summer, now that, you know, exam season is over, at least for me. So yeah, thank you guys for watching, and hopefully this is an exciting prospect that I've laid out for you here. So yeah, see you guys shortly, hopefully. Bye!